So it's a great honor to follow Ed Altman, whose work, of course, I followed since I just myself began to do work in credit risk. And Ed has been a great support to me also over the years. But it's also a great burden to follow Ed Altman because I will not be nearly as entertaining. I'm talking about a relatively technical topic today, and so your adrenaline might flag. So what we're doing here is taking a new look at a rather old problem, the problem of backtesting. And specifically what I have in mind is backtesting of the models that are used to produce value at risk or expected shortfall numbers for your trading book. Okay, so we're thinking about a bank that has a one-day ahead forecast of its P&L, but we're going to talk about loss, so we're just going to flip the sign and think about a loss variable L. I would always warn junior colleagues never to put math on the first slide, and here I'm doing it, and it's because really to understand what we're doing, you have to understand the data that I'm talking about. There's new data that we did not have before. And to understand what that data is and why it's interesting, you just need a little bit of notation because 10 minutes of explanation won't give you a clear idea if you don't really see the math. So we have some information that evolves through time, and we have a calligraphic F as the information set. And each day the bank forms a forecast of its day ahead, the distribution of loss one day ahead, conditional on where we are today. So FT refers to the loss that will be realized on day T, and you're forming that distribution with information at T-1, the day before. You're forming the portfolio at T-1, you're forming your model at T-1, and then reality gives you the loss at T. Now there's a true model, FT, but the bank doesn't observe the true model. We don't observe the true model. The bank is going to use F hat T as its forecast. And the question is, ultimately, is F hat a good model? Does F hat reasonably represent and capture the features of the true model F? Now, in the regulatory context, to answer that question, and actually in bank practice internally, it's generally assumed that the backtest is based on what are called var exceedances or exceptions or violations, meaning a realization of loss above the var that you announced the day before. Okay? So the var hat is what you're reporting. It's for some quantile alpha, which we're going to take to be 99%. The bank is going to report, now here's where we get to the data. The bank will report the var, and the next day report the realized P&L, or the realized loss. Okay? And the exceedance is simply an indicator variable that says, is L greater than var? Now increasingly, and this is really the crux of the paper, regulators and bankers or risk managers internally observe more than just these exceedances, all right? And what they observe is something called the probability integral transform. They may not call it that, but that's what this is. So what it is you take the realized loss, and you see where did it fall in the distribution that I forecast yesterday, okay? What is its p-value, if you will, in that distribution? And that's what I'm calling a PIT, or probability integral transform process is. Say the P up there. And these reported PIT values, if you observe the PIT values, they have information about var exceedances at every possible level, whatever your choice of alpha is. So PT is greater than some threshold alpha, any threshold alpha, if LT is greater than the var for that alpha, even if it's not, this is not necessarily now 99 or the quantile that you're targeting, it's any alpha. Now, if the F hat coincides with the true model, FT, then these PIT values are IID uniform in distribution. And that's the crux of the backtest, right? In the United States, banks have been, on the internal models approach for the trading book, have been required to report these PIT values since about 2013. So the question for the paper is, what do we do with this? We have more information than we did before. What do we do with it? And here's just to fix ideas, what the data might look like. So is this, yeah, all right. So for each day, you get a reported VAR, you get the realized loss, and here you can see on day 5 there was an exceedance. The loss is bigger than the VAR. This final column is the new piece of information, and notice that we observe more than just the fact that it was greater than VAR. We observe actually that it broke the 99.5 percentile of the forecast distribution. And similarly, for the days that are 0, we now observe more than that. We observe more than just knowing that it was below 99. We actually observe what that value was. Now, if you just want to test whether these PIT values are uniform 0, 1, we know how to do that. Frank Diebold and his co-authors back in '98 showed how you do this. And it's a general method for forecast density tests. But in a risk management context, not every quantile of the forecast distribution is really important, right? Some are more important than others. So accuracy in the good tail of the distribution, high profits, which here correspond to low PIT values, that's generally not so important in the risk management context. It's the bad tail of large losses that you're interested in. But if you go way out, 99.99999, most practitioners would say, well, I don't expect my model to be accurate there. The model was not built for that. So maybe those super high quantiles, maybe those are not so important. So what we're going to do is study a class of backtests in which the test introduces weights, and these weights represent priorities. We're going to call these weights, the weighting function is a kernel function, and that kernel function makes explicit the priorities of the tester for which quantiles are important. And one of the lessons of the paper is that there's a trade-off between power and specificity. So imagine, and I don't think this should be the case, but let's start here, that the regulator is really only interested in 99% VAR, doesn't care about anything else, okay? Now, if that's literally true, if you're indifferent to performance at other quantiles, then actually the exceedance indicators that we had already, the 0 ones, those are sufficient because they're targeting exactly what you're interested in, okay? And in fact, our framework, if that's really your kernel function, all the weight at 99, we can accommodate that. It's a special case. So we absorb in our class of backtests almost all of the pre-existing backtests. But if the regulator is willing to assign positive mass to probability levels just around that alpha, just around 99%, you can get a more powerful backtest. You have more information. Now, we even want to step back and take a broader view of what the risk manager should be doing. And really, the way I see it is, the objective is to forecast probabilities over a range of large losses. So if you tell me that a model designed to deliver 99% VAR need not do a good job at the 75th percentile level, I agree. It wasn't built for that. But if you tell me that the bank fails to forecast at the 98.5% level or the 99.3% level, should I really trust that the model can still be successful at exactly the 99% level? That doesn't seem plausible. And in fact, formal guidance of the regulators, certainly in the US, but now in Europe as well, is to explicitly require checking the distribution of losses against other estimated percentiles. What they're talking about is PIT values. So our tests are based on transformations of indicator variables for exceedances, but now exceedances at every possible level. And we call these spectral transformations. We're not talking about spectral in the sense of autocovariance sequences. This is more spectral in the integral transform sense. So the transforms take the form of this W, and I'll be talking about W a lot. Here's your exceedance indicator that the PIT exceeds some U in 0, 1. And nu is a measure defined on the unit interval. Okay? So nu is chosen to apply weight to different levels according to your priorities. And we refer to that as the kernel measure for the transform. Again, thinking about this in the transform literature. And you'll notice that by this second equality, that W is just an increasing function, weakly increasing function of P. It's a distortion of P that captures what do we care about, what do we not care about. And the spectral backtests are just backtests based on these W's. All right? So the null hypothesis throughout is going to be that the distribution of the W's is given by some distribution function fw0 that where fw0, and by the way, IID as well, where fw0 is the implied function for w given that p is supposed to be uniform. Okay, so it depends on the kernel as well. And there are two classes of backtests. Again, this is familiar from the literature. There's the unconditional coverage tests. So there we're just getting, you have over a long period of time, do we have the correct distribution, right, unconditionally? And then there are tests of conditional coverage, which are looking as well at serial independence. Remember, we're supposed to be IID here in this sequence. So the kernels, they can be discrete, they can be continuous, they can be mixed. And I'll just give you a few examples. All right? So when they're discrete, it's really equivalent to saying, is to just putting mass at certain alpha points. So if we had m points, we would have alpha 1, alpha 2, alpha, up to alpha m, and we would assign a weight to each one. Okay? Now the special case of m equals 1, that is just your exceedance indicator, right? And in that case, then the sum of the w's suitably normalized is just binomial under the null hypothesis, and you have your classic tests, your classic binomial score test, and your likelihood ratio test that Kupiak, my colleague Paul Kupiak back in '95, introduced and Christofferson refined. Now the general case gives you a multinomial test, right? These are just supposed to be multinomial in distribution. So you count the number of times that WT takes the different possible values that it can take. It can only take m+1 values. And those count variables jointly should be multinomial with known parameter values. And you have a score test again, and you have a likelihood ratio test again. In the continuous case, what we're going to assume is that this measure is just given by a density function, g, and it's going to be on an interval, alpha 1 to alpha 2, a closed interval that we refer to as the kernel window. And it is 0 outside the kernel window, right? We put no weight outside the kernel window. The kernel window is the important part of the distribution. It's positive inside the kernel window, and it may or may not be 0 at the borders. Okay? So this G is basically, in the non-parametric literature, what they call the kernel function. However, in the non-parametric statistics literature, the kernels are generally normalized and symmetric. We don't need that. You can impose it, but you don't need to. Okay? Now, if we write capital G for the integral of G, you just find that W is just G of P star. P star here is a truncated p-value, where you're taking the max with alpha 1 and the min with alpha 2, right? And it's going to be strictly increasing in p star, okay? And that helps us with the likelihood ratio tests. Okay, so I'm probably only going to have time to talk about the tests for unconditional coverage today. And basically what's going on here is we're just testing that the distribution of the W's has the correct distribution implied by the null hypothesis and the choice of kernel. Actually implied by PIT, the PIT values being uniform and the choice of the kernel. And broadly, the tests just really fall into two types: z-tests, which are normal, distribution tests, or chi-squared tests more generally, and likelihood ratio tests. And I'm going to focus on the continuous kernel case, but it's really no different. So z-tests are based on asymptotic normality of means. So you're taking a mean W hat of your sample of W's, and it turns out that for the null model, no matter how complicated nu is, the kernel measure, we can easily get its expected value and its variance. Well, when you have the expected value and the variance and you know something is asymptotically normal, you've got a test. Central limit theorem gives you this natural test, right? And if there are going to be various multivariate extensions of that will be chi-squared tests, but it's really the same thing, right? And in general, these z-tests are sensitive to the choice of kernel measure, which I hope to show you. The likelihood ratio tests are going to be very different. In the likelihood ratio test, you need a parametric alternative model that nests the null model, okay? So the idea of the test is that there's going to be some parameter vector theta in your parametric model that recovers the null hypothesis distribution, okay? And theta hat is going to be your MLE estimate, and then you do the conventional likelihood ratio, right? Now it turns out, and this is surprising at first, but natural if you think about it a little while, it turns out that the LRT, the likelihood ratio test, depends only on the support of the kernel measure and not on the weights. It's indifferent to the weights. Only depends on the support. And the reason is, and it's a well-known result, the likelihood ratio test is invariant to a strictly increasing transformation of the data. And our W's are strictly increasing, under continuous kernel, strictly increasing transformations of the truncated PIT values. Therefore, it's indifferent to the G. The only thing that counts is the kernel window. Another key distinction is that the z-test is easier, right? When you do an LRT, you've got to estimate the nested model, the more general model, excuse me. So for the z-test, what it's going to depend on here, I have 10 minutes? Okay, good. There's kind of a nice result here, a product rule. Let's say we have two kernel densities, continuous kernel densities on the same window. And W with a J subscript is for each the corresponding PIT, transformed PIT value. It turns out the product is also a spectrally transformed PIT value, and its density is another valid density on alpha 1, alpha 2. And that is going to be the way that we get the variance, because if W1 and W2 are the same, then the new W star is just equal to W squared, right? And therefore, it's easy with this formula to get the expectation. You just have to integrate out over the U. And these things are, in general, for typical kernels, these will all be closed form and very easy to work with. Okay? So the spectral z-test follows immediately. We can generalize it. Why just limit ourselves to one kernel? We can maybe get a more powerful test with two kernels, although that does break a little bit the intuitive connection to what the tester is worried about. So if we have two distinct kernels on the same support, we use the product rule now to get a vector, mean vector, and a variance matrix, and you just end up with a chi-square test. Right? And we can take this to J kernels if we like, whatever you like here. Now, in the likelihood ratio test introduced by Berkowitz in 2001 that's still very influential, there's a transformation that we can also use in spectral tests. And what you're really doing is you're assuming that the P are probitnormal, that the normal CDF inverse of P maps back to something that's normally distributed, right? And what you're doing is you're testing that the mean is 0 and the variance is 1. That would correspond to the uniform distribution for the PIT values, all right? And the likelihood function as closed form expression, and the score vector, as always, is just defined as the derivatives of the log likelihood with respect to the parameter vector. And it turns out that has analytical expression. And it also turns out that the score can be written as a vector of spectrally transformed PIT values. It's a little tedious to write out, but what it means is that this score test, which is a very traditional statistical test, really just is a special case of our bispectral test, okay, that we can write out. And we can also, of course, do the likelihood ratio test. That's also going to be trivially a spectral test. And it generalizes the Berkowitz test in the sense that Berkowitz was proposing to test over the entire tail, whereas we're saying, well, you may not want to go out to the very far reaches of the tail, and it still remains tractable. So we're going to do a parametric simulation study to look at the power and size of these tests. And the way this works is that you sample data from 4 different distributions that will represent the true data generating process. So we have a normal and 2 t distributions, a skew t, all distributions scaled to have mean 0, variance 1. And of course, these other t distributions have fatter tails and higher value at risk. Now, what we're going to assume is that, just for the sake of the simulation, that the risk manager is assuming that the world is Gaussian. So f hat is just the normal distribution, even if the true model could be normal, but could be t. Okay? Now, where f is normal, the actual data here should be uniform, and what in effect, we're doing is looking at the size of the test. And otherwise, P will show departures from uniformity that would be typical when the tail is underestimated, and that's showing the power of the test. So we'll look at a bunch of discrete kernels, bunch of continuous kernels, and I'll sort of summarize quickly what we get out of that. So with the discrete kernels, we're looking at 1, 3, or 5 points. When it's 1 point, it's just the standard binomial score test on var exceedances. Otherwise, we've got, with these 3 and 5 point tests, we've got various multinomial tests and spectral tests that differ in terms of the weight put on the points. I've ZU to weight them uniform and ZE to sort of increasing weights. And what you find is the size is very good with all these tests. These numbers all come around 5%, it's fine. And the power is below. And what you see is that compared to the traditional binomial test, we always do better. The uniform test doesn't do much better, but it does somewhat better. Not a big difference between 3 points and 5 points. And what you see is that among the spectral tests that the exponential one does really, really, really well. Now you would think, that's great, let me use the exponential kernel. Well, you have to think there about what's driving that. It turns out that the standard binomial test gets more and more powerful as you move further out in the tail. And this is showing you for various, true models, when you assume a normal f hat, what the power of the test is. And what you see is a couple of things. First, that it's not monotonic in alpha, that actually the worst alpha point is around 98. Turns out to be very hard to reject alternative models at 98. Okay, something I didn't know. But it really increases here quite a bit. The problem is your tests are becoming more erratic. I mean, if you're out at 9999 and testing that, one exceedance out of 1,000 data points, 4 years of data, is enough to reject, right? You're likely to get 0 or 1. So the statistic becomes quite erratic, and its properties are not very good. But my point here is that if you're doing an exponential weighting, an exponential kernel, then really you're just giving very high weight to points out here, okay? So you're basically, it's almost like doing a binomial test, but at a much higher quantile. And if that's what you'd wanted to do in the first place, you should have done that in the first place, right? So this is just a way to reinforce the idea that when you choose the kernel, you don't want to just chase power in the test. You want to think about what you're doing. 3 minutes. Okay. So with we're going to have a similar set of kernel densities for the continuous case. And one thing the only thing here I really want to emphasize is that, again, we have an increase in power. We do much better. Z lower e is a decreasing exponential function. Z capital E is that increasing capital function. And as you would expect, this one does far better, ZE, capital E. But what's interesting is that the bispectral tests do better than either of them, right? So essentially, with the bispectral test, which is really quite a bit more powerful, what's going on is, in effect, we're looking at multiple moments of these transformed data, and that's what's giving us the additional power. Now, the next thing that we do, and I don't have time to get into the details, but to develop tests of conditional coverage, and in effect, this is a generalization of Engel and Maganelli's well-known dynamic quantile test, or sometimes called the caviar test, where you're using the fact that anything that is currently your information set when you form the forecast should be orthogonal to your error, your forecasting error, basically. And if it's not orthogonal, you'll pick it up in this test. And what we're going to find is these Martingale difference tests are quite powerful. When most banks, as you know, use historical simulation, they should be, in my view, using Giovanni, I don't think he's here today in the audience, but his filtered historical simulation. Historical simulation, these tests are extremely powerful in rejecting historical simulation. And it's because of the serial dependence due to unmodeled stochastic volatility that's what gives it its bite. So the rejection rates are quite high for the MD tests. For filtered historical simulation, you can reject, but the rejection rates are nowhere near as high. So, just to summarize then, these tests based on spectral transformation of the bank's reported PIT values can yield quite a bit more power than the traditional simple var exception tests. And what's nice is it's a strictly broader class. I mean, we don't, the only well-known tests that fall outside of our framework are the duration-based tests or the spacing tests that work by looking at the time difference between your var exceedances. Other than that, pretty much everything is going to fall in our class. And by expressing tests in this form, it forces you to think about the implied kernel. It forces you to think about what is important to me. What am I trying to test? What part of the distribution do I actually care about? And I think, from my perspective, just that process of thinking about it is a valuable discipline. Finally, I have the data. I happen to work at the Federal Reserve, and we have a couple of years of these reported PIT values. They are distressingly dirty in many ways. I mean, there's a lot of data cleaning to be done, but that work is in progress. And next time I give this talk, I'll have those results. Thank you.
Thank you.